Transition metals are a group of elements located in the D block of the periodic table. They are known for their characteristic properties, including their ability to form colored compounds, complex compounds, and their variable oxidation states. This ability to exhibit multiple oxidation states is a key characteristic of transition metals and is responsible for their activity and versatility in forming compounds. In periodic table, the elements are arranged based on their electron configurations and chemical properties. The transition metals series includes elements from group 3 to group 12, with the exception of helium and zinc. The first two rows of the D block elements, scandium to zinc, fail the 3D orbitals, while the subsequent rows, yttrium to cadmium, fail the 4D orbitals, and so on. One of the defining characteristics of transition metals is their partially filled d orbitals. These orbitals enable the transition metals to form complex compounds with ligands, which are molecules or ions that donate electron pairs to the metal. Transition metals are generally good conductor of heat and electricity, and they have high melting and boiling point. They often exhibit lustrous and shiny appearances, and they are malleable and ductile, meaning that they can be hammered into thin sheets and drawn into wires respectively. Transition metals have a wide range of oxidation states, meaning they can lose or gain different numbers of electrons to form ions with various charges. This property allows them to participate in redox reactions and act as catalysts in many chemical reactions. Many transition metals and their compounds display vivid colors. This phenomenon arises from the absorption and re-emission of light in the visible range, giving rise to the vibrant colors often associated with transition metals compound. As for example, copper compounds are often blue or green, while iron compounds can be yellow, red, or green. Some common examples of transition metals include iron, copper, nickel, zinc, titanium, and chromium. These elements find wide-ranging applications in various fields such as constructions, electronics, medicine, and transportation due to their diverse properties and versatile nature.
Transition metal role. Transition metals play a crucial role in energy production due to their unique properties and reactivity. Here are some key roles of transition metals in various energy production technologies. Firstly, catalysts. Transition metals often serve as catalysts in energy-related reactions. They can speed up chemical reaction without being consumed in the process. For example, platinum PT is used as catalyst in fuel cells to facilitate the electrochemical reaction between hydrogen and oxygen to producing electricity. Next, electron transfer. Transition metals can easily transfer electrons, making them available in energy storage and conversion devices. In batteries, transition metal compounds such as lithium-ion batteries enable the reversible transfer of electrons between the positive and negative electrons, storing and releasing energy. Third one, photovoltaic cells or solar cells. Transition metals are used in the development of photovoltaic devices such as solar cells. They can serve as components in light-absorbing materials or as conductive layers. For instance, titanium dioxide (TiO2) is a commonly used material in dye-sensitized solar cells (DSSCS), acting as a photoactive layer to convert sunlight into electricity. And the last one is hydrogen production. Transition metals can be catalysts in processes related to hydrogen production. For example, transition metal catalysts like nickel or iron are used in hydrogen evolution reactions, which involve the splitting of water into hydrogen and oxygen using renewable energy sources. Overall, the unique electronic structure, catalytic activity, and redox properties of transition metals make them essential components in various energy production technologies, contributing to the advancement of renewable energy, energy storage, and more sustainable energy systems.
Fuel cells are electrochemical devices that generate electricity through the conversion of chemical energy from a fuel and an oxidant. They operate based on the principle of redox reactions and utilize an electrolyte to facilitate the movement of ions. Here is a brief description of a fuel cells. As for the structure, fuel cells consist of several key components. These include anode and cathode electrodes separated by an electrolyte. The electrodes are typically porous to allow for the flow of gases, and they are often coated with catalysts to facilitate the electrode reactions. As for the electrode reactions, at the anode, a fuel such as hydrogen gas or methanol is supplied. The fuel molecules undergo a specific electrochemical reaction depending on the type of fuel cell to release electrons and produce positively charged ions. The electrons are forced to flow through an external circuit, generating an electric current that can be used to do work. At the cathode, the oxidant, such as oxygen or air, is supplied. The oxidant reacts with the electrons that have traveled through the external circuits and combines with the positively charged ions that have traveled through the electrolyte. This electrochemical reaction typically produces water as a byproduct. As for the electrolyte in a fuel cell facilitates the movement of ions between the anode and the cathode. It allows the positively charged ions to pass through while preventing the passage of other molecules. The electrolyte can be a solid, liquid, or a polymer membrane depending on the type of fuel cell. Moving on to the catalysts. Catalysts are used at the electrodes to enhance the electrochemical reactions. They lower the activation energy required for the reactions to occur, increasing the efficiency of the fuel cell. Common catalysts include platinum for hydrogen-based fuel cells and various transition metals for different types of fuel cells. As for the efficiency and environmental benefits, fuel cells offer high energy conversion efficiency compared to traditional combustion-based technologies. They operate without combustion, resulting in reduced emission of greenhouse gases and pollutants. Hydrogen-based fuel cells in particular produce only water as a byproduct, making them environmentally friendly. Types of fuel cells. There are various types of fuel cells, including proton exchange membrane fuel cells, PEMFC, solid oxide fuel cells, SOFC, molten carbonate fuel cells, MCFC, phosphoric acid fuel cells, PAFC, and direct methanol fuel cells, DMFC. Each type has different operating temperatures, fuel requirements, and applications. Fuel cells have various applications across different sectors due to their efficient and clean energy conversion process. Here are some notable applications of fuel cells. Firstly, transportation. Fuel cells have the potential to revolutionize transportation by providing a clean and efficient alternative to internal combustion engines. Fuel cells vehicles, FCV, use hydrogen as fuel and convert it into electricity through a chemical reaction. FCV offer a long driving ranges, shorter refueling times compared to battery electric vehicles, and zero emission operation. Secondly, portable power. Fuel cells can be used to power portable electronic devices such as laptops, smartphones, and cameras. Portable fuel cells offer longer runtimes and quicker recharging compared to conventional batteries. They are particularly useful in situations where access to electrical outlet is limited or unavailable. For the backup power, fuel cells are employed as backup power systems for critical facilities, including hospitals, data centers, and telecommunications infrastructure. These systems provide reliable power during grid outages, ensuring uninterrupted operation and minimizing the risk of service disruptions. Stationary power generation. Fuel cells are used in stationary power application to provide electricity and heat for residential, commercial, and industrial buildings. They can be integrated with natural gas pipeline or utilize renewable fuels to generate clean and efficient power on site. Fuel cells in combined heat and power configuration can also utilize the waste heat produced during the electricity generation for heating or cooling purposes. As for the remote power, fuel cells offer a reliable power source for off-grid and remote locations where access to electricity is limited. They are utilized in remote monitoring systems, weather stations, off-grid cabins, and telecommunication infrastructure in remote areas. Fuel cells can provide a continuous and self-sustained power supply in these environments. For the military applications, fuel cells are employed in military applications for powering equipment and vehicles. Portable fuel cells provide soldiers with lightweight and long-lasting power sources for field operations. Fuel cell-powered vehicles offer quiet operation, reduced heat signature, and extended operational range, making them suitable for military use. And lastly, marine applications. Fuel cells have the potential to replace traditional internal combustion engines in marine vessels, such as boats and submarines. Fuel cell systems can provide clean and quiet propulsion, reducing emissions and environmental impact in marine environments.
Solar cells. Solar cells, also known as photovoltaic cells, are devices that convert sunlight into electricity through the photovoltaic effect. They are made of various materials including semiconductors, which can absorb photons from sunlight and generate an electric current. When it comes to transition metals, they are not typically the primary materials used in solar cells. However, transition metals and their compounds can play important roles in enhancing the performance of solar cells through different mechanisms. Here are a few examples. First one, catalysts. Transition metal complexes can act as catalysts in solar cells, particularly in dye-sensitized solar cell (DSSCS) and photoelectrochemical cells (PECS). These catalysts help to facilitate the chemical reaction involved in the conversion of light energy into electrical energy. Next, doping. Transition metal can be used as dopants in the semiconductor materials of solar cells by introducing small amounts of transition metal atoms into the semiconductor materials into the semiconductor lattice. The electrical properties of the material can be modified, leading to improved efficiency and performance. Third one, transparent conductive electrodes. Some transition metals oxides, such as indium tin oxide (ITO) and fluorine doped tin oxide (FTO), are used as transparent conductive electrodes in solar cells. These electrodes allow light to pass through by providing electrical conductivity. And the last one, thin film solar cells. Certain thin film solar cells, technologies such as copper indium, gallium selenide CIGS, and cadmium telluride CDTE solar cells may incorporate transition metals within their absorber layers. These metals help optimize the absorption of light and improve the efficiency of the solar cell. Actually, its importance to note that solar cell technology is a rapidly advancing field, and new materials and techniques are constantly being explored. While transition metals may not be the central component in most solar cells, their incorporation in various forms and contribute to enhancing the efficiency, stability, and overall performance of solar energy conversion devices. Limitation of chemical transition metals in solar cells. One of the limitations of typical transition metals in solar cells is their low electrical conductivity. Transition metals, such as iron, nickel, cobalt, often have moderate to low conductivity compared to other materials commonly used in solar cells, such as metals like silver or indium tin oxide (ITO) for transparent conductive electrodes. The conductivity of a material is crucial for efficient charge transport within a solar cell. When sunlight is absorbed by the active layer of the solar cell, it generates electron-hole pairs. These charge carriers need to be collected and transported to the electrode interface to generate an electric current. However, if the transition metal used in the electrode material has low conductivity, it can hinder the movement of charge carriers and lead to higher resistive losses within the device. How to improve this limitation? Researchers employ strategies to enhance the conductivity of transition metal-based electrodes. For example, they may use techniques like alloying, doping, or forming composite materials with conductive additive. This approach can improve the electrical conductivity and thereby reduce the resistive losses, resulting in more efficient charge collection and improved overall device performance.
For the transition metals in batteries is using a lithium-ion transition oxide, and it is one of the typically rechargeable battery materials, and it has played an important role in adapting and improving battery technologies for the commercialization. It is typically utilized as positive electrode materials in the lithium-ion batteries such as lithium cobalt oxide, lithium manganese oxide, lithium nickel manganese cobalt oxide, and lastly lithium nickel cobalt aluminum oxide. This is due to its unique properties, which is acting as an abundant active site, short diffusion pathway, low preparation cost, high specific capacity, and distinct reaction mechanism. In a state of charge in the battery, there is a cathode containing lithium cobalt oxide that is migrating the lithium ion to the anode. The anode then containing graphite to receive lithium ion to form graphite intercalation compound. From the equation from the equation, we can see the cathode is also releasing electron which undergo in the oxidation state, and the anode is receiving electron which is in reduction to maintain the stability of the both electron. For the discharge state of the battery, reversible, reversible reaction takes place where the lithium ion from the anode is migrating to the cathode, and from the equation, the cathode now is receiving electron which undergo a reduction process, and the anode now is releasing the electron. However, there is a limitation in this typical transition method in batteries such as lower end of charge voltage, small energy and power density, and shorter life of the batteries. So, to improve the performance of these typical batteries, we need to conduct synthesis of newer type of transition metal oxides where it has more advantages than conventional lithium cobalt oxide. Secondly, we need to modify the existing lithium cobalt oxide to improve the energy and power density of the battery. And lastly, we need to conduct a research on the surface coatings and coating methods to increase the end of charge voltage of the lithium metal oxide. In conclusion, transition metals has proven to be a critical role in energy-related technologies devices due to its unique catalytic activity and semiconductor properties compared to other non-transition elements. Various chemical reactions can take place involving transition metals because of their de Broglie properties, which make it a very important substances on Earth. It also helps humans to continue evolving their technologies for a better future, such as in energy production technologies like fuel cells, batteries, solar cells, and etc. Moreover, the evolution of these technologies is very important to improve the quality of energy production and making the energy production more greener for environment because of its high powered, cost effective, and environmental friendly.